Welcome back, everyone. Today we're going to start on our work on Chapter 3, dealing with functions and inequalities. So 3.1, we do a little review of functions. So first we start with what it takes to be what's called a relation. So a rule that connects one set to a second set is a relation. So that one, pretty low bar to clear. All you have to have is two sets. You remember all that work we did in Chapter 1 on set theory. Pick one first set, one second set, and make some rule connecting the two of them. You've got a relation. That's all it takes. So sometimes the rule is some mathematical relationship. Sometimes it's described in words. Sometimes it's physical properties. For example, we looked at Fahrenheit Celsius conversion. Those are based on just physical properties. So sometimes our rule is actually written in mathematical symbols, sometimes in words. Now, a special subcategory of relation is a function. If each element of the first set corresponds to exactly one element of the second set, then the relation is also a function. Now, the way we use domain in single variable equations just meant the universal set of answers. Now, since we really have two sets with two different domains going on, we changed the vocab a little bit. So the domain in the first set we will continue to call the domain, but the set of values in the second set will now be referred to as the range. All right, so let's look at an example of a relation, decide if it's a function, and how we know it's a function. So we'll look at the relationship C is equal to 5/9 of F minus 160 over 9. So this is the temperature conversion formula, solve for the variable C instead of solve for the variable F. So we can identify a few pieces of this. We have two sets involved and some rule connecting them. This is a relation. Our domain variable that would be our set of input variables, in this case, F degrees Fahrenheit. Our range variable is C degrees Celsius. And some type of rule. Our rule in this case, multiply input by 5/9 then subtract 169ths. Now, since there's no way to take an input value, multiply it by 5/9 and get two numbers, or take that answer and subtract 160 over 9 and get two answers, this relation is also a function. So it clears both hurdles. We have a rule connecting them, and that rule maps every single object in the first set into exactly one object in the second set. All right. So onwards and upwards. So next we'll work with what are called mapping diagrams. Mapping diagrams give us a visual representation of the rule rather than a formula for the rule. So in this case, our rule will just be shown with an arrow. And we have a domain as a starting point, a rule, and a range. So we'll start with a domain of 0, 1, 2, 3, and 8. Range values of 0, 1, and 2. So 0, I'm going to map that to 1. You do need the arrows if you're making your mapping diagram. They do have to be pointing at the range, not at the domain. 1, I'm going to map that to a 0. 2, I will map that to a 1. 3, we'll connect that guy up with a 0. And 8 will be matched up with a 2. So we have two sets, a domain and a range, and we have a rule, so automatically this is a relation. That's all it takes to be a relation. Two sets and some rule connecting them, even if in this case the rule is just a whole bunch of arrows showing you where to start and where to finish. But the bigger question is, does this qualify to be called a function? Well, remember, for a function, every input value corresponds to exactly one output value. Well, my input value of 0 corresponded to 1, exactly one value. An input value of 1 corresponded just to the number 0. That works still. 2 corresponded with 1, 3 corresponded only with 0, 8 corresponded only with 2. Every single item in the domain went only one place in the range, so this also is a function. So it does meet both criteria. All right, let's look at a new mapping diagram. Domain, rule, and range. So our domain this time, let's do 0, 1, and 2. And we'll go with A, B, C, and D. All right, so 0, I'm going to connect that with, we'll pick C for that. 1, we'll connect that with an A and with a D. And 2 is going to be connected with a B. So first off, we want to know, is this a relation? Well, I have one set called the domain mapped into one set called the range, and we have some type of rule connecting them, so this is a relation. Next, I check to see if I have a function. So 0 goes exactly one place. 0 goes to C. 1, though, 1 is matched up both with an A and with a D. I have one element of the domain going to more than one place in the range, so this one is not a function. So 1 corresponds to both A and D. Now that's all it takes to derail it. It might go to 100 places. It might go to 1,000. All I have to show, though, is 2. That's our work with mapping diagrams. So next we work with some functions that are written with formulas but have sort of a smaller domain than what we're used to. So on this one, I'll start with a domain containing elements 0, 1, 2, and 3. And we'll have the rule that we multiply each domain value by 7, then subtract 20. So in this case, then they're leaving it up to us to figure out what the range looks like. But we can make sort of a similar chart. So domain, I'll list out our values, 0, 1, 2, 3. Our rule in symbols, if the domain, if we decide to call those, typically we would call those X. Our rule will map into a range value. We'll typically call that a Y. So our rule, our range value is found by multiplying each domain value by 7, then subtracting 20. So there it is in symbols. So for the first one, Y is equal to 7 times 1 minus 20, which is 7 minus 20. So a range value of negative 13. Our next Y value, 7 times, my apologies, that was supposed to be the 0. I'll do the 0 here, and we'll just sort of switch these two rows. My apologies. 7 times 0 minus 20 is 0 minus 20, negative 20. Our third Y value, 7 by 2 minus 20, turns into 14 minus 20. So a range value of negative 6. And finally, Y is 7 by 3 minus 20. 21 minus 20, a range value of positive 1. So one way to express that rule is to just call it by the symbols. Y is 7x minus 20. Another way is to give the function a name. So functions can be named. Now in math, when we're just using generic ones, f, g, and h are the most common names. So I might call this function f of x. 7x minus 20. So f of x is my range value. So f is the name of the function. X tells me the input variable, sometimes also called the independent variable. And then we have our rule on the other side. So notice here, f of x, this does not mean f times x. F is just telling you the name. X is just telling you what thing to treat as your input. So you've seen that a little bit in some of your previous coursework. So our next one will start in function notation. So we'll try g of x is equal to the square root of the quantity x minus 7. So our domain variable on this one, also called the input, also called the independent variable, and this one is x. If it were a word problem, I'd also state what x meant. Our range variable in this case is g of x. Again, if it were a word problem, I'd state what g of x actually meant. This is also sometimes called the output variable, also sometimes called the dependent variable. And our rule in this case, remember, order is important when you have multiple operations. So on this one, radicals with an operation within them do count as grouping symbols. So we would start there. So subtract 7 from the input, then take the square root of the result. Alright, so let's try one where we put a few numbers to it. This one we'll call h of x, and we'll call it x minus 11 quantity squared, and a given domain of, well, let's do 0, 5, 10, and 15. So if I want to make a mapping diagram, our rule here, h of x, x minus 11 quantity squared, range value, and one other thing that is sometimes useful, they also have us work with ordered pairs. Just a shorter way to represent which values are related to which other values. So we'll start with the domain value given of 0. So our rule then would be h of 0. So notice here I'm plugging in whatever domain value they gave me. So this is no longer h of x, and at this point it's h of 0. h of 0 is 0 minus 11 quantity squared, which is negative 11 quantity squared, positive 121. In an ordered pair, 0 was my input, 121 was my output. And we can, of course, repeat that with the 5, 10, and 15. h of 5 would be 5 minus 11 quantity squared. So that is negative 6 quantity squared, so positive 36. An ordered pair would be 5, 36. So here I recommend pause the video, see what you can do with the 10 and the 15, and play it when you're done. Okay, welcome back. So with the 10, h of 10, 10 minus 11 quantity squared, which is negative 1 quantity squared, which is positive 1. So 10, 1 is an ordered pair for this function. With the 15, h of 15, 15 minus 11 quantity squared, which is 4 squared, positive 16, so 15, 16 is also an ordered pair for this function. Occasionally we do have to restrict the domain. This is sort of bringing us back to the idea of excluded values that we've worked with before. So they might give us p of q is 24 over q plus 2. If they initially give us a domain of, oh, let's say -4, -3, -2, +1, and +2, we may have to restrict the domain. So running through these, I'm checking for, since this is a rational expression, I'm looking for division by 0. And notice our friend here, the -2, would give us division by 0. So in my restricted domain, that will no longer appear. So our restricted domain is now the set containing -4, -3, 1, and 2 only. So after that, the problem works pretty much the same as before. I recommend pausing it, seeing if you can find, create for yourself a similar chart to what we had above there. Okay, welcome back. So our domain here, restricted domain, we had a -4, we had a -3. We skipped over the -2 since that gave us a division by 0 issue, a +1 and a +2. Our rule for this one, P of Q, was 24 over the sum of Q and 2. That will let us have a range value, and we can make ordered pairs out of it. So we'll start with P of -4, so that's 24 over -4 plus 2. Remember your order of operations. An operation happening in the numerator or denominator counts as grouping symbols. So I've got to take care of that first. 24 divided by -2 gives us a range value of -12. So our ordered pair here would be -4 for the input, -12 for the output. And we go through the similar things with the rest of it. P of -3, 24 over -3 plus 2, which is 24 divided by -1, which is -24. So we have -3, -24 as well. P of 1, 24 over 1 plus 2 is 24 over 3, which is an output of 8. So 1, 8 is also an ordered pair for this function. And finally, P of 2, 24 over 2 plus 2 is 24 fourths, which is 6. So 2, 6 is also an ordered pair on this function. So here we all try one more out. So I'm just going to give you the rule and have you create the rest. So f of x is going to be the square root of the quantity x minus 5 with the stated domain of 4, 5, 6, 9, and 14. Okay, so pause the video, see if you can recreate what we did on the other pages, find the domain, the rule, the range, and hint, you may need a restricted domain. Okay, welcome back. So restricted domain, this time we're underneath a square root. Smallest number that we want underneath the square root is 0. If I plug that 4 in there, I get into negative territory. That means 4 is one of our excluded values on this problem. So our restricted domain contains 5, 6, 9, and 14. So then we'll do our domain, our rule. In this case, our rule f of x is square root of the quantity x minus 5, our range, and our friends, the ordered pairs. So our first non-excluded domain value 5, we would find f of 5. So square root of 5 minus 5, which is square root of 0, which is range value of 0. Ordered pair would be 5, 0. We'll repeat that with a 6, f of 6. Square root of 6 minus 5, which is square root of 1, which is a range value of 1. So 6, 1 is also an ordered pair. Next we jump to the 9. And see if you can figure out why I skipped all the way from 6 to 9. So square root of 9 minus 5 turns into square root of 4, which is a nice pretty 2. So 9, 2 is another nice ordered pair there. And again, see if you can figure out why I went from 9 to 14 without including anything else in between. So 14, 3 is also an ordered pair for this particular function. Okay, so that should give you enough ammunition to work your way through section 3.1. Really try to spend some time with it. 3.2 really assumes that you have 3.1 down cold. Really try to put some time into it. Please email me with any questions that you have, any problems that you're stuck on, and I'll get back to you as quick as I can. So again, this was section 3.1. Get in touch with me with any questions. Stay safe out there. Try to stay in as much as you can, and hope to see you as soon as this is over.